Right, hello all again. Again, these videos, I'm trying to make them quick so you can pause and reverse and whatever, but try to make it short and sweet. Alrighty. Then remember Unit 2 and how it started. Linear functions, of course, are y minus y1. My pen's not working. Equals m times x minus x1. Just wanted to explain why this looks like it does times x minus x1. That's point slope form. Then just add y1 to both sides. I guess why they call it yi, I don't know. But that was an arithmetic sequence, and this takes on the same form where we have a common difference, a kth term, and then how far are these two terms away, n minus k. That just means this is how many common differences this term is away from that one, right? But it really takes the same format as this. Then geometric functions are exponential, not linear, and they take on this form, which is this form. Some ratio times some term turns into that term, and that's how many ratios you have to multiply by to get from one to the other. Okay, so hopefully you can kind of remember that from back in the day. And then questions that pertain to that, you'll just have to wait till you see examples and how that works, and we can probably work through that in class. All right, exponent rules we see here, big one, negative exponent rule. The other one I like is the zero exponent rule, which is equal to 1. That's because this comes from like b to the third divided by b to the third. We know that's equal to 1. But if I take 3 minus 3, I get b to the 0. That's why these are equal to 1. And then the fractional exponent rule, being able to know that this ends up being b to the first, the kth root of that. So the denominator is the kth root. Then we had a lot of questions that pertain to that. That's not really the purpose of this video, just to remember your general ideas here. Then when you actually take the practice test, you put them into action. All right, here we go. We got exponential growth. Now they're saying a equals 1. I guess it could equal 2, 3, 4. That'd be a multiplier that vertically stretches. If it was 1/2 for a, then it vertically shrinks. But it doesn't matter. If this b value is greater than 1 and this is a positive, you're still going to have an increasing scenario exponentially. And then take a note to these limits. I don't know why some of you could not figure out these limits to save your life. As you plug in a value for x positive, this y value goes off into infinity. That's what this means. The y's go off into infinity. Oh, my bad, dogs. I thought about this. I was going to say, like, hey, let's pretend we have an actual specific function. So when I plug in 0, 3 to the 0 is 1. When I plug in 1, I guess we should do 2 here because it looks like this goes to 2 right there. So it looks like the y equals 2 raised to the x function. Then when I plug in 2, that becomes 1, 2, 3, 4, which it does look like that's at 2 comma 4. But why I did this is what happens when I plug in -1? I don't have time to explain this. We should know this. 2 to the negative first is a half. 2 to the negative second is a fourth. So what's happening as I plug in negatives? You get values that never make 0 but get darn close. So what we do is we put a horizontal asymptote there, y equals 0, and then denote that behavior with a limit statement. As I plug in big negatives, the y approaches 0 on the left. All right, and I'll highlight that in green. Some people never really figured that out, and I don't think that's a very bad concept. All right, but then when this is a fraction, like y equals 1/2 raised to the x, I plug in 1, I get a half. I plug in 2, I get a fourth. I plug in 0, I get 1. I plug in -1, flip, 1/2 becomes 2. So that's why it's very simple input output. So easy, right? But now when I go ahead and look at the limit, as this goes to negative or infinity for x, we approach the 0 fractions, the fractions that are getting close to 0. And then as we plug in big negatives this way, the y's go off into infinity. So some people really struggled on those limits. I don't understand why. All right, and then when we get negatives for a, we got flippage over the x-axis. So just to cover these limits, as I throw in a huge X, the Y goes to negative infinity. Got it circled right there. As I plug in a big negative X, you're getting to that 0 value for Y. And then if you have a fractional, I mean, look at this. I'm trying to slide this up. There we go. So this flipped over. So that's what that graph is here when I throw this being a negative there. Bad English there, but anyway. Then we're approaching 0 as I plug in big X's. As I plug in big negatives, I get a negative infinity for the Y value. So where this is going is what this answer represents for those that never connected with that. All right, and then E. Remember, E is approximately 2.718, just for giggles, if you want. Write that down. But it's that natural base for growth and decay in nature and in money. It's crazy. So that's why the number is so important. And then transformations. A is a vertical stretch or shrink. H is a right-left shift. K is an up-down shift of these situations. This is kind of weird. I will mark this. This is pure AP kind of questions. And this relates to this rule. 2 to the third times 2 to the second equals 2 to the fifth. You add these exponents. So reverse that. So if I had this, I guess I should write this as 3 plus 2, and that equals 2 to the fifth. Because what this is doing is reversing that concept. Now let's understand, this is a variable. K will be a number, like x plus 1, let's say, or x plus 2. So if this said x plus 2, then this would be b to the second. And b to the second, b will be a known number. So what this will turn into is some sort of multiplier out in front, right? And then that's what this says right here. This is writing it in different forms. What does this horizontal translation turn into? A vertical dilation of some sort, depending on if that number is greater than 1 or less than 1, in between 1 and 0, I should say. And then this is just the usage of the, let's use x. X to the third raised to the second. You multiply those exponents. 3 times 2, so that's x to the sixth. So when you look at this, they rewrite this backwards. And then what we could evaluate then is B and C will be given as numbers. You could go ahead and recalculate that. And what that did was change the base. So it's no longer B is the base. Whatever B raised to the C is as a number is the base. So we did have a lot of questions like that. Again, you'd have to see an example when it comes up, and then hopefully we can cover that when it comes. All right, and then this is just, instead of doubling every day, turning it into weeks. How many days are there in a week? 7. Now again, if I multiply these two, then I would get 2 to the D, so it'd be equal. We're just writing this in a different form, and whatever 2 to the 7th is, that's our new base for a weekly scenario. All right, and then I guess we'd have to look at residual plots here. They kind of reference it. I'm just going to give you a real quick idea. It's like when you do a scatter plot, pretend you had a parabola and your data was like this. This means this data is pretty good to this scatter plot. What a residual plot does is linearize this graph, and it shows the data points. This point would be here. This point would be here. This point would be here. And that's what you want in a residual plot. No pattern, but the points are kind of around this. Imagine if the data points were like this, showing a linear pattern, and I had a parabola that went through this. This is terrible. These on that residual plot would be like this, and then they would be like not even close to that line. So what you want is a scatter that has no pattern where they're all around. When this skews away, this means the residual plot is showing a bad regression model for the scenario. So I did want to cover that real quick because they just kind of mention it. So you want a model that has no pattern. This is a pattern of going away from the residual model. I'm sorry, from the model. This is a residual plot. I used that term wrong. All right. Fogg and Goff, these are doing composition of functions. This is when you plug one into another. Hopefully, when we see examples, if you need a question on that, go for it. When I say inverse, you say switch x and y. So if you had something simple like this, 3x plus 1, how do I find the inverse? You switch x and y, and then you resolve. That's a linear. I tried to make this exponential real quick as I try to rush through this. And again, I'm going through this fast so I could get this to be a 15-minute video tops so that you understand like certain concepts. Subtract 1, divide by 3, and you get that inverse of that one. Okay, and again, this is review, so these things should spur memories. And then if you do have a function and its inverse and you do a composition of those, you will end up just getting x. And hopefully you remember that as well. Not sure that'll end up on the exam or not. We'll see that as we go. This is the definition of a logarithm. Base, exponent. So this is the base. This is for what a logarithm means, the exponent. And then I just called this the answer. But the true term for it is argument. But I called it answer. Okay, and then that's where the argument goes, or the answer to an exponential scenario, and that's where the exponent belongs. So to change a logarithm to an exponent or exponent to a log, that's all you got to do. Logarithms and exponential functions are inverses of each other for sure. Whoa, I don't know what happened there. Right, and then that statement right here is logarithm functions are always increasing or always decreasing, so they don't change. There's no extrema. So this is when your b is greater than 1, and it's because of this. Like, let's pretend, what does it look like? This does look like a log base 2. And I'm going to remind you of input output on log base 2. When I plug in, well, I can't plug in 0. Log base 2 of 0 doesn't exist. 2 to what power equals 0? None. That's why you have a vertical asymptote. I would draw that right now. Right? But then log base 2 of 1, what is log base 2 of 1? 2 to the 0 power. That's the power right there. 2 to the 0 power equals 1. So y equals 0. That's why I get 1, comma 0. Then the other one I'm going to plug in is log base 2 of 2. 2 to what power equals 2? 1. So I plugged in 2 and I got 1. There we go. I can plug in one more, I guess, just for fun, because this is a blast. Log base 2 of 4, 2 squared equals 4. So I plugged in 4 and I got 2. And look at that. It does look like that graph's there. Input output, classic. All right, notice this logarithm's limit statement. 0 plus. That means to the right of 0. You're right. That plus means right of 0. Again, this is review. This should spur a memory. And when I'm just right of 0, my output's way down here. So that's why this is negative infinity. But when I plug in big numbers for x, these y's are going forever off to infinity. So again, the limit statements are going to be huge. If I turn this into a fraction, then we just have this flipped as a decreasing graph. All right, and I'm just going to reference the limits as we're getting at 14 minutes on this video. 0 plus means input, output. Very large for an output. Oh, sorry, a little scratchy throat these days. Logarithm rules. Logarithm of a product becomes a sum. Power raised to a power rule. You pull this out in front. Division means subtraction. All right, so, oh no, that's not what this is. Sorry. Hold off on that. Don't cross that off. I don't know why they don't have this. Log base B. Sorry. A divided by B is log base B of A. I need a drink of water. This is great for the video. Log base b of, oh, it's funny that I did log base b of b because that equals 1, believe it or not. But anyway, we'll just leave it. All right. Oh, and I have it actually even here. This equals 1 as well. That's strange because b to what power equals b? 1. But don't worry about that. Okay, then I love this. How do I know this is exponential? Because the outputs go up by a multiplier of 2. What? Hold on. Sorry, that's wrong. 2 times what is 6? What am I doing here? 6 at 3. Oh my gosh. What is happening here? So that first one should be a 3. I think this chart is wrong. 1 to 2, 2 to 6, because that multiplies by 2, then this is by 3. So I think we have a problem here. So this is a mistake on the thing here. So let's just leave this here, times 3 times 3. And I think we have a problem here. So that's definitely wrong unless I'm missing something. Because here, this does make sense. When the x's have a common multiplier. Yes. So I caught a mistake in the notes. Right? 1 times 2 is 2. 2 times 2 is 4. 2 times 4 is 8. When the x's have a proportion, then it's logarithmic in data. So you had a lot of questions where you had to look at data on a chart and figure out if it's logarithmic, exponential. On my previous video, we had one for polynomials with x squareds. Second order differences are equal. Hopefully you get the idea there. All right, and then equal functions just by doing some math. So it's using our logarithm rules. So this is just the sum rule. Product becomes a sum. Then what we're saying is b and k will be given. So I will be able to evaluate what that is. So this multiplier on the inside of this function turns into an up-down shift. And that's what that manipulation told us there. All right, and then this one, when I pull this power out in front, this becomes a vertical dilation number. Oh, and then they finally showed the division rule. That's weird that they put that there. Okay, and then that also shows vertical dilations of each other as we can read that sentence. All right. Yeah, solving equations and inequalities. We're trying to remind you that'll be a big component. And again, when we get into the actual test, we'll see, if you need help on those. Definitely a huge component of our year. That's a big thing. One thing about checking your answers, especially on a logarithm, you cannot log a negative number. That's all you really have to check. And you actually cannot log 0. That is, I just showed that up there before. Say if this is base 10, and by the way, that is base 10 if it's invisible. We should remember that as well. 10 to what power equals 0 doesn't exist. No answer. No answer. 10 to what power equals a negative number? Impossible. Impossible. Okay, and then we did do a lot of data modeling with that, and that would be in the calculator section. Those might be in our FRQs. We could talk about that when we talk about FRQs. All right, and then semi-log plots. It's logarithmically scaled. So remember that like 0 to 10 goes up by 1s. So here's 0 to 10. Then the next ones go up to 100, if you remember. So then the next lines go up by 10s. So 0, 1, 2, 3, 4, 5, 7, 8, 9, 10, then 10, 20, 30, 40, 50, 60, 70, 100. Then the next lines go up to 1,000. So this is 100, and then 200, 300, 4, 5, 6, 7, 8, 9, 1,000, and so on and so on and so forth. And what it does to a logarithmic graph that would look like this on a regular coordinate plane, it makes it look linear on a logarithmically scaled semi-log plot. All right, and that was the big idea there. Again, you'll have to see examples of that to, really get use out of this. So when you actually do your practice, try to remember these things. Hopefully this spurred some memories. But when you get to specific things, then you'll see what we're talking about here.